Okay, so now I will present task 1. Derive the mathematical model for question A. Okay, so for task 1, we derive the mathematical model for the pollutant concentration. We start with the differential equation. This by splitting the variable and integrating both sides, we obtain the general solution. That is Ct equal to Co exponent E negative Kt. Okay, using the given data, this where the initial concentration is 250 mg/L and the concentration after 6 hours is 129 mg/L, and we calculate the decay constant as 0.08513. So therefore the final mathematical model is Ct 250E negative 0.08513. For the question B, find the time when the concentration reaches 50 mg/L. Okay, so we determine the time when the pollutant concentration reach 50 mg/L. So we substitute 50 into the model this one. So we divide both sides by 215, giving exponent negative 0.08513t equal to 0.2326. Next, we take the natural logarithm of both sides and solve for t, and the calculated time is 17.13 hours. This means the pollutant concentration will reach the target value of 50 mg/L after approximately 17.13 hours. Okay. For task C, the graph illustrates the relationship between pollutant concentration and time. So the graph show an exponential decay pattern. The concentration decrease rapidly at the beginning because the pollutant level is high. As time passes, the rate of decrease becomes slower and the concentration gradually approaches zero. From the graph, we can observe at the concentration is 129 mg/L at 6 hours and reaches 15 mg/L at approximately 17.30 hours. Finally, for task D, the exponential decay model demonstrates that the treatment process effectively reduces the pollutant concentration over time. Initially, the concentration decreased quickly, but the rate of reduction slowed down as the concentration becomes lower. Based on the model, the target concentration of 50 mg/L is achieved after approximately 17.30 hours. So, this behavior is consistent with many natural purification and water treatment processes where the rate of reduction is proportional to the existing pollutant concentration. That's all for task 1. Thank you.
So, this to give a distinct real roots. So, because of this, we use the general second order solution is QT equal to A exponent negative 76.45t plus B exponent negative 1923.55t. So, as we know that the Q0 equal to 2 times 10 negative 6 and A plus B equal to 2 times 10 negative 6, and then we just get the formula to find the B first, and the B will get 0.083 times 10 to the power of negative 6, and from this equation, from this value, we put inside this equation and we get the E equal to 2.03 times 10 negative 6, and this is our final formula. Alright, so for test 2, we use this equation and the constant given this 0.34 and R equal to 680 ohm and C equal to 20 microfarad, and then we use this equation, and then we divide this equation by 0.34 and we get this, and then from this we change it to the quadratic formula, and then we get the S1 equal to negative 76.45 and the S2 will get the negative 1923.55. For the question B, so B, we need to evaluate the response at 0.01 second, so we just put the value here and we'll get the value, the final value is 9.698 times 10 to the power of negative 7. So this is our graph based on the equation. So for discussion, we have three discussion. We mean over the nature, the discriminant of the characteristic equation is positive. Is confirmed. The classic over them respond without any imaginary component, indicating zero oscillation. Transcedulity, the system features a two-part decay. The large root handles the rapid adjustment right after t equal to 0, while the small root determines the slower long-term rate at which the module settles. So for the engineering component, for the data acquisition modules, this non-oscillating decays avoid voltage overshoots or signal ringing, ensuring clean data login.
Alright, right now I will do a task 3. So the function is 23 minus 1.5t, and now and the t is 23. The interval is 0 until 23. So right now we want to find the a naught, so we just 2 over 23 integrate with 23 minus 1.5t, and then a naught 22 over 33, we just integrate it, and the answer of the integration 529 minus 396.75, and a naught is equal to 11.5 and a naught over 2 is equal to 5.75. Right now we want to search an. We just use 2 over 23 the function and cos 2n pi t over 23, and we integrate it. 23 integrate cos 2n pi t over 23 and minus 1.5 integrate with t cos 2n pi t over 23, and we let k is equal to 2n pi over 23, and then we just integrate one by one. We integrate cos kt and we got the answer is 0, and we integrate t cos kt. We use integrate by part, uv minus integrate with u, and we got here, we got it here, and after we differentiate this, then we solve, and we integrate from the answer is we integrate from this, and we integrate, so we solve until this equation, and we got 1 over k square and 1 over k square, and we minus 1 over k square minus 1 over k square is equal to 0. And we substitute back in the equation, and we got n is equal to 0. We looking for the bn 23, and we use a sign. We integrate one by one. We integrate sin kt dt, and we got 0, and we integrate t sin kt. We use integration by part. We solve, and we integrate it, and we got negative 23 over k and then we substitute in the equation, and we times with 2/23, and we got Bn is equal to 34.5 over 2n pi. And for the question B, take n is equal to 1, 2, 3, and the function, the answer is 5.75 plus 34.5 over pi, and sine multiply sine 2nt over 23, and plus 17.25 over pi sine 4 pi t over 23, plus 11.5 over pi sine 6 pi t over 23. And for the C, L is equal to 23 and T is equal to 23 over 2, and we got T is equal to 11.5, and we put the 11.5, and we got F 11.5 equal to 5.75, and D Ft equal to 23 or minus 1.5t, and T we use T from here 11.5, and we substitute, and we got 5.75, and looking for error, 5.75 minus 5.75